Hello and welcome. My name is Piers, Ridyard, CEO of RDX Works, a core developer of the decentralized finance protocol Radix, a public ledger entirely focused on bringing DeFi into the mainstream. Today, we have Dan Hughes, founder of RDX Works, and we are going to be talking about a paper that has just been published in a peer-reviewed journal, the Journal of Systems Research, JSIS for short. And the paper title is Cerberus: Minimalistic, multi-shard, Byzantine resilient transaction processing. So, this has been in the work for a long time, Dan. So could you give us a little background behind what this paper is and why you've been working so hard on it?
Yeah, so this paper it's an extension of the original paper. Well, we've had two papers really. So we had I think it was 3 years ago, the Cerberus document that was up on the website for a while, which was more of a technical document rather than a paper, I guess.
Yep.
Which it kind of laid the fundamentals of what Cerberus is as a cross-shard communication consensus protocol. And then we had an actual paper that we published, which we put together, and UCD and Professor Story helped us out a lot with. Another Yale Hellings was also, pivotal in putting that paper together. And that paper was decent. It got published on Archive. It's been cited a bunch of times, which is good. But we always wanted to undergo peer review as well, right? That was a decision that we took internally. And so this paper is the result of that peer review process. So the actual kind of consensus mechanism that is Cerberus, that does all the cross-shard comms and handles all like failures and bringing validator sets to a quorum, hasn't really changed much. But the paper has grown significantly because we've improved the definitions, we've improved the explanations, we've improved the proofs, we've done further analysis, we've ran simulations and test networks against other consensus mechanisms that are, cutting edge, high performance, etc., etc. So this paper is much more extensive. So if you really want to dig in and understand Cerberus, then this is the paper that you should read because it's a lot clearer. It goes into a lot more detail around what is Cerberus, what are the different flavors of Cerberus, what does it do, what are the edge cases, what are the failure cases, what are the assumptions, and all those things. And this has been a labor of love now for quite some time.
Yeah.
I think we first submitted to a journal maybe 2.5 years ago.
Yeah.
And at the time, I think things have moved on a little bit now, and there's a bit more acceptance for blockchain, crypto, consensus protocols. But back at the time, we were getting rejected from a lot of journals because it didn't fit what they wanted to discuss or publish as a topic, right?
It was also COVID hit right at the time.
COVID hit as well, yeah. So that just extended the timeline for us to get the rejects, right? Usually you would get one in, say, a month or so. But in some cases, we were waiting up to 6 months to get the decision of, no, sorry, this isn't for us, which is fine, right? It just means that it's pushed out this peer review quite a lot.
Yeah.
And then finally, we landed on JSIS, and the problem is as well with peer review papers, you can't submit to multiple journals at the same time, right? You can only submit to one, and then you've got to wait what the decision is there. If you're not accepted, then you can find another one that hopefully you think will be favorable to this paper. You submit to them, etc., etc. So finally, we got to JSIS and we published to them, and we like JSIS because JSIS is quite new as well. It's not quite as established as the other journals, but they're a lot more open to different problem sets, and it's an open review as well, so you can see the reviews at the end of the process. You can follow what's going on. It's all public. It's all open, which is quite nice.
Yeah.
And so you can read the feedback on the reviewers, and you can look at the revisions that we've made over the past 18 months or so. And you can see that communication backwards and forwards between us and them. And the peer review is obviously blinded as well. So nobody knows. The people who are reviewing don't know who the authors are. They don't know the name of the paper was different. Cerberus was changed in all the paper to have a different name and stuff. So
What was
It's completely.
what was the different name?
Well, I mean, it was quite close because it was Chimera, which is another three-headed thing.
Right.
So, yeah, we didn't change it that much. But nobody knew that it was, me, us,
Yeah.
UCD, etc. Um,
And
and
like
then,
this, and you say that it's quite different. It is basically completely rewritten. If you go and if I go and like flick through the paper that's on archive, um, the previous one, the ones that we call the maths proofs paper, and I look through this one, this is probably two or three times, or at least two times longer,
yeah, it's a lot longer.
significantly more citations,
Yeah,
and a lot more sort of like graphing around the testing of different instances of Cerberus. So there's sort of like optimistic Cerberus and pessimistic Cerberus, and a bunch of sort of like different uh, formulations of the same model. There's also some throughput testing in here as well, right?
yeah.
So could you talk a little bit more about the throughput testing and what sort of the throughput testing did or did not show about Cerberus?
Sure. Yeah. So this is probably the main thing that was missing from the original paper, right? Was this testing against other consensus mechanisms and testing of Cerberus itself, etc., etc. And we definitely needed that for a good peer review process, right? We need to have the analysis. You need to be comparing to other state of the art consensus mechanisms, so that and those tests need to be apples to apples, right? As much as you can do. And so we had these instances of Cerberus, instances of Sharper, instances of AHL, and all the ones that are in the paper.
Yep.
And in order, and this is interesting because actually this has come up quite a few times in discussions about permissionless, right? I've seen some chatter on Telegram and on Twitter about what does that mean for permissionless? And permissionless is really a civil problem. It's not really a consensus problem, right? The permissionless aspect of it is, how do you make sure that the bounds that break consensus aren't easily breached? Yeah. So how do you make sure that your civil mechanism is protecting the upper bounds of the consensus mechanism so that you don't have safety breaks and Leibniz failures and stuff like that, right? From a consensus point of view, consensus doesn't care who's voting, who's creating the proposals. It works the same either way, right? If you take proof of work out and put some public key infrastructure in place for Bitcoin, it'll still work the same, right? You'll have to emulate proof of work somehow, or
Right.
have a slightly different mechanism. But the core consensus of Bitcoin, which is strongest chain rule, that doesn't change, right? As long as you can create blocks that have some element of strength, then you'll be fine and it'll still work. But what permissionless allows you to have is dynamic validator sets, essentially, right? Where people can join, people can leave at will, and makes it very difficult to take control of a large portion of the network.
Right.
So that's permissionless, yeah? And in the tests, it was much easier to do a permissioned Cerberus than it was to come up with some form of permissionless Sybil mechanism that would work with all of the other consensus mechanisms that we were testing.
Right.
And we weren't testing Sybil, we were testing consensus. So, okay, well, let's just use the same Sybil mechanism that we would use for these other ones, which is permissioned,
Right.
because what we're really benchmarking is consensus. We're not benchmarking Sybil. So if we were to put permissionless compatible Sybil on top of all of these consensus mechanisms, then sure, some of the things would change, right? The throughput would change, the latency would change, but the ratio of performance difference between Cerberus and all of the other consensus mechanisms, Cerberus would still come out on top, right? It just adds a scalar to it instead. It doesn't really change the outcome of the results.
Right.
So, and we didn't want to build or come up with tests where we had permissionless Sybil that was compatible with all of these other consensus mechanisms. Instead, we just decided, okay, let's just adopt that Sybil mechanism, which is just permissioned, and use it on Cerberus instead.
And so what was the, just for those who haven't read the paper, could you summarize what the results were of sort of like Cerberus versus AHL, Chainspace, Ring BFT, and Sharper?
Yeah, I could probably do this from memory, but I'm going to reference the paper just
Sure.
in case. I mean, I've seen this enough times, but I'll probably end up making a stupid mistake. So basically, if you look at these graphs, which are on page 19, then you've got various different configurations, right? You've got different configurations, number of shards, number of transactions, how many shards those transactions touch, etc., etc., etc. And basically, the result is the same across all of them, right? So the black line is core Cerberus, which it makes quite broad assumptions on faulty actors in the network, what the transaction load looks like, etc. Right. So that really is core Cerberus is really just testing the communication protocol between shards. You probably wouldn't use that in any kind of deployed network out in the wild unless you could make sure that the assumptions it makes can hold. And I think that would be quite difficult. But in all of the tests, C Cerberus comes out top, right? So what that tells us in the test is that the core Cerberus communication protocol between shards is the most efficient. Yeah, it's the most efficient, not just in the family of Cerberus variants, but it's also the most efficient across all of the consensus mechanisms that we tested that deal with sharding. Then you've got optimistic Cerberus, which the main assumption that this makes, so it can tolerate, faulty actors and stuff like that, but it makes an assumption that there won't be any concurrent transactions, right? So, for example, you couldn't easily build a DEX on optimistic Cerberus because you might have lots of concurrent transactions or a liquidity pool. Yeah, you'd have lots of concurrent transactions that are trying to do a trade that would change the price, and that price is a piece of state, and so it can't deal with concurrency, and it has quite a crude mechanism to recover from that if it does detect any concurrent transaction, any concurrent transaction trying to touch a particular piece of state. So it's quite crude. So again, unless you can satisfy those assumptions, you wouldn't use O Cerberus. But if you are sure that you're not going to ever have any concurrent transactions, or if that's not a problem, then you could use O Cerberus, right? And then the final one, which is the one that we're obviously going to use, is P Cerberus, which is pessimistic Cerberus. So O Cerberus is optimistic because it makes an assumption that there's not going to be any concurrent transactions, so it can be more optimistic in its processing. P Cerberus doesn't make that assumption. It's like, okay, there could be concurrent transactions, there could be faulty nodes, there could be Byzantine modes, failures, validators dropping off, coming and going, whatever, right? And P Cerberus can handle all of those cases. Now, obviously, as you can see from the graphs, C Cerberus is quickest, then it's O Cerberus, then it's P Cerberus. And that's basically because of this fault tolerance, right? The fault tolerance costs you something. And in our case, there's a cost, but it's fairly negligible, right? In the grand scheme of things. But you can see from the graphs that the more shards we have, the throughput is linear. Now, there's a little bit of a dip at the beginning, and I've seen some chatter about this. And that dip at the beginning is purely because it's an efficiency thing, right? So if you think about, okay, I've got a processor that can handle say it's got 8 cores in it, right? And I'm not able to fully use those 8 cores because there are some concurrent pieces of state that are being used at the same time, or the throughput and the load into the network isn't actually saturating across all of the shards at any one moment in time, or I've got a lot of lock-in, or the nodes are busy. And this usually happens at the lower shard numbers because those nodes, those validators get saturated on. You've got a lot of throughput coming through, but they can't process anymore because they've got various objects locked in those shards and they can't do anything about it, or they're just at saturation in those shard groups. So this is where you get the dip. But then as you increase the number of shard groups, it's more load balanced, it's more efficient. You can pipeline things better, so it's more efficient as well. So that's where you tend to get this dip at the beginning. And then once you're past the dip and everything is as efficient as it can be in terms of your load, your distribution of load across all the shards, the number of shards that you have, you can see that, and it goes linear.
And this is and so basically, if you extended this out for the actual target shard space 2 to the power 256, you would see that after the dip, the linear would just maintain.
It would just continue.
right?
Yeah, indefinitely.
So
Yeah, you
what
could
we're
put,
seeing here is basically the start of the hockey stick for linearity, but like you're only seeing part of it because the scale was not tested out to 2 to the power 256 shards. It was only tested out for 2 to 10 shards at 64 objects, and at 64 objects per transaction, you're looking at a large amount of potential congestion. That you have this waiting time until you've got to the point where you have enough shards to allow parallelization. And one of the many reasons that we picked, 2 to the power 256 or like a very, very large shard space is because you only see the optimization of parallelization in the shard space as you go to very large shards, as you get large throughput on the network. Because if you actually, the scale on the side is actually pretty large. 10 to the power 6 is a million transactions per second, right? So like we're looking at charts here that go beyond a million transactions per second tested across 2 to the power 10 shards. Now, obviously, you can scale it in both directions, and scaling it up on the throughput and scaling it across on the shard space, you can see how you get that linear relationship between the two.
yeah. I mean, one interesting thing with these graphs is that as you increase the number of objects per shard, what that kind of manifests in here is you zooming in on the dip, right? So in the first one, the 2 objects transaction, you don't really have a dip at all.
Right.
Yeah, Chainspace has got a bit of a dip, but we don't really have any kind of dip. But then you go to 4 and you can see that we're starting to dip a little, and then 8 it dips a bit more, and then 16 it dips a bit more. And by the time you're up to 64, you need to have greater than 2 to the power of 6 shards for your, the efficiency of the communication and all the validators, etc., to overcome the inefficiency of the load it's being presented with, right? But you're kind of zooming in. So if you thought the other way, if you just increase the number of shards that you have and you were zooming out instead, then you would just see that linear line. And if you zoom out far enough, you can't even see the dip, right? It just goes up linearly.
Right.
And you get the same effects if you increase the number of replicas per shard as well. Replicas in this case is what everybody in crypto calls nodes, validators, whatever, right?
Right.
It doesn't really change very much. Like there is some additional overhead, of course, because you've got more communication going on. You've got to do more signature validation, which you could optimize away to a large degree. This paper doesn't talk anything about optimization of signature aggregation and verification and that kind of stuff, even though a lot of people now have been working on that on the side. So the disparity between these two graphs, the 7 replicas and the 61 replicas, you can reduce that to some degree. But the point is that it shows the same curves, right? The curves are the same essentially. Yeah. If you've got 61 replicas per shard versus 7, you get almost exactly the same looking curves across
Almost
the board,
exactly
and
the same looking
still
curve.
exhibits that linear scalability once you get past the kind of efficiency discrepancies around the load it's been presented with and the communication overhead.
And how did you guys...
Eventually the communication overhead gets more efficient as well if you're maximizing the number of things that you're putting into a proposal, right?
Right. And how did you guys sort of choose 7 replicas per shard versus 61 replicas per shard? And how did you guys choose the number of objects per transaction?
There wasn't really any kind of discussion really around that. It's just, what can we do? We don't want to spend too much money. Right? It's like, what kind of tests can we do that cover a wide range of scenarios and show 2 different scenarios with different replicas with the same type of load and stuff. And so it was just really, what hardware availability do we have? What cost do we have? How much time do we have between us to do these things? And so that's kind of what we came up with. So they are a little bit arbitrary, but it's fine, right? Because it shows what we wanted it to show, and you can see the linear scalability in both cases. So if you were to go to 200 replicas per shard and some different combination, you went to more shards, more objects, a transaction, etc., and you were to run those tests, you would just see the same kind of outcome.
So I think the other question that people will ask looking at this is Chainspace is obviously we're all of the Cerberus instances are outperforming Chainspace, but Chainspace maintains a pretty close relationship. So could you talk a little bit about the similarities and differences of the Chainspace approach versus the Cerberus approach?
Yeah, so Chainspace is very interesting because it exhibits linear scalability in the same way, right? So what the graphs are showing for us is that while they achieve linear scalability too, and it's interesting that they also have that exact same inefficiency as well on the drop off, right?
Yeah.
But what the graphs are saying to us is that Chainspace has linear scalability, but their communication protocol is less efficient than Cerberus, right? And remember, these graphs are logarithmic, not linear. So when you're at the top end of the graph, even though it looks like the difference is small, it's actually quite big, right? Because if you were to do a linear graph, you would see the Cerberus family of consensus mechanisms accelerating away from the Chainspace, right? So Chainspace is kind of moving up like that, and the Cerberus family is going a bit more exponential because they're logarithmic graphs. So that communication inefficiency over time, overload, number of shards, number of objects per shard, etc., it just exaggerates and exaggerates. So by the time you're in the upper ends of linear scalability, Cerberus is doing, hundreds of thousands, if not millions, more transactions per second than Chainspace for the same amount of for the same configuration. I mean, in terms of what's different, Chainspace is a two-phase commit. It has a bit more communication complexity between the groups. What's interesting as well is that it has a different means of aborting from transactions that are under adverse conditions as well, which can add quite a bit of latency. Then some a bit of like a not really a recovery period as such, but it's overhead that it needs to deal with. What else is there's something else as well? I mean, the differences are fairly minor, to be honest. It has largely the same kind of operating mechanisms that we do. You've got this cross-yard communication. Use a lot of the same primitives. It's just that the main difference is that our setup is a bit more efficient in terms of communication and message complexity. So, but then that makes a huge difference, right?
Right. And so now this is done, paper's out. We've gone through the peer review process. We've tested the transaction in sort of academic test conditions to sort of millions of transactions per second. What's the next phase for this?
So in terms of Cerberus as a cross-yard communication pattern, there's nothing really to do now, right? I mean, if anybody finds any issues in the paper, then we do have the option to make minor changes, right, which would be good. Because we don't, even though it's been peer reviewed, it's a big paper and little things, spelling mistakes or things that are just slightly wrong may have been missed, right? So if anybody has any of them, find any, do let us know. But in terms of further work on the paper and expanding the description of Cerberus, we're there, right? Finally, thankfully. So really now the next step of this is Cerberus is essentially parked, and I'm now working on the local consensus that Cerberus sits atop, right? Which many of you know is the stuff that I'm researching with Cassandra, to find a more efficient means of being able to have a local consensus process that isn't like hot stuff is fine, but there's a lot of complexities that arise from using hot stuff when you have a massively sharded architecture, right? Because it's leaderful, doesn't have any kind of liveness guarantee under partial synchrony or asynchrony. It makes assumptions, or probably the main assumption that it makes to deal with that is that if some validators leave, eventually they will return, right? And that's obviously not always the case. There is a diagram in the paper that shows where Cassandra will where currently hot stuff would sit, and I think it's towards the top. Is it somewhere? God, this paper is huge. Now you have to scroll a lot to find what you're looking for. It's on page 2.
Yep.
Page 2, and there's a big green Cerberus box, and then you've got like a light yellow box and a purpley box. And you can see here they say PBFT, not hot stuff, right?
Right.
And the reason that says that is because we wanted to make a point that doesn't really matter what sits underneath Cerberus. All Cerberus cares about is that whatever consensus mechanism is local in the validator sets, that consensus mechanism spits out and can support certain primitives that Cerberus requires to do the cross-shard stuff, right? So that could be PBFT, it could be hot stuff, it could be something else, or in my case, what I'm now researching, obviously, is Cassandra, which removes some of these inefficiencies and complexities around the assumptions that are made, leader selection,
Validator set
changes,
size.
all these things that just add a lot of complexity. And so that's probably going to be the next 6-month grind to a peer review, hopefully, on Cassandra. But the more immediate goal is to get a draft of that paper out before Babylon lands in July. So my 2 goals really for the past 6 months up to Babylon was to get Cerberus through peer review, and then to get a draft on archive of Cassandra consensus.
Yeah. So
we have one, which has taken longer than I hoped it would. So I've got a bit of a grind now on the Cassandra paper.
Fantastic. Well, I mean, I think I speak for everyone when I say, sort of huge congratulations on getting this through peer review. It is not an easy path, especially if you don't have an academic background. I mean, I don't know how many people know this about you, but you didn't go to university, let alone do a PhD or anything like that.
You didn't go to college either.
You didn't go to college, exactly. So like everything you've got is basically from secondary school, and then from self learning onwards. So being able to take yourself from self-taught, GCSE, high school level schooling to the point where you can write an academic paper that gets into a sort of a well reputed academic journal, and through the rigors of peer review process, I think is that definitely deserves congratulations.
Thank you very much, dude. Thank you. Yeah, I mean, I just knew what I wanted to do, and I just wanted to get straight into it, when I left high school. And I didn't really have any means to go to college, especially, and definitely not university, right? And there wasn't all the benefits that we have now either, right? There wasn't really much in the way of grants or support. People, a lot of people know, but I came from a very poor background, so opportunities were thin and far between. So I figured the best way was to just hit the world and learn what I needed to learn, and go from there. Maybe one day I'll do a degree.
You don't need to. I don't know why you'd need to.
I'll sit in Professor Satogi's class and he can teach me some stuff.
Yeah, exactly. So congratulations, Dan, and the team that you've worked with. And if anyone hasn't checked it out already, it's on the Radix blog. If you go to radixdlt.com/blog, you'll see a blog post entitled Cerberus Consensus Peer Reviewed, and from there it will take you to the various materials that allow you to jump into the final peer reviewed paper.
One final thought, actually, with regards to Chainspace, I guess. And I always felt that it could have been something, and it now isn't, and it isn't used anywhere. And I have a lot of respect for the guys that put that together, because it's a really strong protocol, and it does share a lot of similarities with Cerberus. And it's interesting that Chainspace and Cerberus kind of emerged at the same time, right? Remember,
right.
we were getting through the Cerberus details, and then I can't remember if it was Josh or Florian stumbled across Chainspace way back when, and we had a look, and it was like, oh shit, this is really close to what we're doing.
Yeah.
And then obviously Meta, but hats off to the Chainspace guys for sure.
Yeah. I think it was. I think it's one of those. It's a great example of simultaneous emergent ideas, right? Like when the world, like the core insight there was that the right thing to do when you want to shard state is UTXO based sharding rather than account based sharding, because you can't really shard account balances. So like that, then you end up in
You
this
always have
situation
contention on the balance.
where you can't do the throughput. So the direction that Ethereum had gone was basically its own little cul-de-sac. But I'd say that, Chainspace was one team that was looking at UTXO based sharding. We were another team looking at UTXO based sharding. And like, to be fair to them, Cardano as well. Cardano is sort of, they have gone down there a different little cul-de-sac, sort of dead end in that. But they also similar understanding of going, actually UTXO is a better state system to use.
Yeah, they have all the EUTXO stuff.
Yes, exactly.
But then what they really needed underneath was explicit finality, which isn't there.
Yes, and they also don't have the concept of they don't have the concept of intent-based consensus, right? So like on Radix, you have this idea of declaring what you want to do, but not saying which state you're going to use to do that. Yeah. That's up to the node runners and consensus to sort that out. Whereas in Cardano, you have to also express,
be explicit about, here's what I'm going to use and this is what I want back. Yeah.
Right, which then creates a lot of problems when you have contentious state around uncontentious intention, right? So like, I didn't actually care that it was that particular EUTXO that I used. I just generally wanted this number of tokens, but because the network is forcing me to choose the EUTXO, if someone else chooses the same one, I end up in this contentious state situation, which Radix completely avoids by having this sort of this layer of indirection between what is expressed at the user intent level and what is done at the consensus level.
Yeah, Radix has this. Oh, you know what I mean? Just do it.
Yes, exactly. That's the end state that I desire.
Yeah.
To work
okay,
out.
do it. Just do it. You know
I
don't
mean? Care how it happens. Just sort it out. Right.
Yeah.
Right. Which the entire crypto space is starting to move more towards as well. Intent based transactions.
It has to be, right? It has to be. There's too much complexity for it not to be for your developers, let alone your users, to understand that. Right? It's extremely difficult as a developer to deal with explicits in these very, mature, expanded networks. Now you've got layer 2s and layer 3s on the horizon, and it's like you can't be explicit, and especially when you've got things like liquidity pools and flash loan, all these things. They're intent-based applications, so you need to be able to. You can't use explicits when you're communicating with them, and if you have to, then you're going to have a lot of complexity, and complexity equals bugs, and bugs equals people losing money, and the story.
Yeah, and this is part of the genius of the transaction manifest, right? It's like the transaction manifest is that programmable layer that allows you to express intent plus guardrails for that intent. You can say, I want this to happen, but I only want it to happen within these set of parameters, and that no one else has that. No one else has that ability to express both intent and the invariance on those intents, so that you can say, I want this to happen, and I want it to happen within this bound. And I think that's going to is critical for user friendliness, but also from the point of view of like making sure that, as you say, developers don't need to care about this. The people that care about it are the people who are actually running the network, and they care about it from the point of view of specializing towards efficiency in ordering all of these transactions, and that's fine. That's that part of the network.
That's where it should be. That's where that complexity should be. There, nowhere else.
Right. Cool. All right.
Cool. Nice little tangent there at the end, Piers, I think.
Indeed. Cool stuff is happening in lots of places. I think
all
that my final thought on this is, as always, is like the whole stack of Radix is what makes Radix special. Like, Cerberus on its own is interesting, The Radix engine on its own is interesting. The transaction manifest on its own is interesting. Scripture on its own is interesting. The Radix wallet on its own is interesting. But it's really the fact that we have designed everything together, that every single one of our engineering decisions have been based around this idea of understanding what the whole is going to look like. And I think that that's really what makes everything special. So you can say, this particular form of consensus performs better under this particular sort of set of specific circumstances. But it's like, well, that specific set of circumstances isn't what we're optimizing for. What we're optimizing for is mainstream DeFi. What we're optimizing for is massively scalable atomic transactions across multiple applications in a way that the user doesn't have to care about what shard they live on, and the developer doesn't have to care about what shard they live on, and the network is able to optimize at the level it's supposed to, and you're able to get linear scalability for all of that. That set of optimizations means that, yes, you can pick specific scenarios where you go, this is better than that in this specific scenario. But we have made these decisions based on what we're trying to get to as an end state.
Yeah, I agree. The sum of our tech is what's the
greater than the parts.
What's the phrase?
The sum is greater than the hot parts.
That's it.
The whole is greater than the parts. Yes.
Dumb moment. Sorry.
Yeah. Yes. It's all right. You've been banging your head against the wall for a very long time. In deep land,
this has been draining, really draining. I mean, it's been going on for a while, but the past 4 months, 5 months, getting through this and trying to push the Cassandra stuff forward, and having a newborn, of course, just absolutely draining. So I'm gonna slow down a little bit this week and just breathe. Because and then push again for we're in good shape to get a paper draft just before Babylon lands, and so this and that, the timing should be spot on.
Awesome. All right, thank you very much, Dan, and enjoy your rest.
Yeah, if ever I get any real rest, sure.